evening. Hope we're all doing well. Um, it's quite late today, and I really want us to touch a lot. I'm afraid of something. Really afraid of saying we're going to get to how some. I wish we could take it to at least half of the course material. This
Don't wish, oh. Let's do, oh. Don't wish, oh.
yeah, that's what I'm trying to do. I'd like us to take it that way. We might
Don't
probably
worry.
exceed 10. Don't worry. We might probably
Don't worry.
exceed 10 today. So as we
Okay.
keep, we're expecting people right now. So in a few minutes we'll start. What's
No,
this?
I think
9
we should
o'clock.
start by
I think
9.
we should
It's 9 already, sorry. It's 9
start
already.
already. And people coming and I'm really even starting from the beginning again. I'm starting from the beginning of the course material. That's why I'm thinking maybe few people should join us more before starting.
Yeah, okay, no problem. I've sent the link though. So people will join soon. Jeffrey of Lagos, I greet you. Kingsmate,
Now, good evening. Oh.
I greet you, boss.
What did they happen now?
And the thing when they happen with the see now.
I just they see only Owola before, yeah.
You know, saying be boss on his own. See how he be. Blackish.
All I've been a showman, always showing. I don't know what he wants show.
I don't
I want make you see now.
I don't mean I dey see my six pack.
No, say Olabi is searching. How you want taxi?
No, it's my wife. She never gives. I see the toast her.
Always well.
Ali Abeg, start. Since you are starting after, let's start from the beginning. So before a lot of people join, at least they'll catch up with where you stopped before.
Yeah, I think I concur too.
All right. Let's start there. Let's go with it. Sorry, I'm trying to reply some important text. Okay, let's start then. Kingsmate, I'd like you to observe my board. Is it okay this way, or I should take it back to portrait? Is it okay this way? Kingsmate, is it okay this way?
No, take it back to portrait. Thank you.
Okay.
It looks like it's upside down.
Abdullah, why we go? Okay. It's physics 102 here.
Please, hello.
Going to
Excuse me. So there's this light reflection on the board. Please don't write there because the last time we did that stuff, I did not say anything.
I can't hear you.
There's a reflection on the board there, the light. Please don't write on it.
Is there really
Yes, because I cannot see it to that thing. Yes.
Okay, just let me
Thank you.
I'm also looking at the board. I'm looking at the board from my phone. Is there any okay. I've known the part. This one is the last part the top.
All right.
You have to, and I'm not writing there, don't worry. That's just it. I'm not writing there. Observe what you are saying.
The refractive index of the light is disturbing him.
Leave it the way it was before.
I'm using 3 different lights.
Yeah. The first one, leave that first one. Leave it the way it was before. The first one is okay. Leave it the way it was before.
I don't confuse you.
The reflection is too perfect now.
Just manage it, I beg. Okay. So, talking about this, Phy102, we know it is electricity and magnetism. Electricity and magnetism. You all know what electricity is, right? So it emerges from electric charge. That is the most, or the earliest form and the earliest aspect of electricity being dealt with, being studied, electric charges. So it was due to what is named Benjamin Franklin and this man, what's he called? Charles Coulomb. So they did so much work. Benjamin Franklin in the 18th century and Charles Coulomb, I don't know his own century. So they did so much work on this electric charge of the thing. And after that, they were able to predict stuff and they were able to get how things come up. So after their own work, Tesla, Faraday, Eddy, and the likes, they all the electrons moving around. So the thing here now is introduction to electric charge. Let's take it that way. Introduction to electric charge. It's a natural phenomenon. Charge exists in the clouds. So when lightning occurs, thunder, when there is thunder and lightning occurs, so there is a very large amount of current, about 20,000 watts. That's about 20 watts of current being discharged. Please mute your mic. Mute your mics. Okay, yeah, okay.
Please.
Okay. All right. I think it should be a little bit better now. So there is a very large release of electric current. So that is due to the charges present in the atmosphere. So when there is a reflection of the sound produced by clouds and the hills over there, different hills, big hills, then there is this churning sound we are hearing. Some of those ones are quite useless at the moment. Let's just talk about what we'll be talking about. Electric charge. It is the fundamental thing that carries, or it is the basic concept of electricity. Electric charge is the basic concept of electricity. That's just it. There is a body right there now. I think I have presented this thing before. This is a marker. I'm bringing this marker towards the sleeve of my clothes, or the lid of the marker towards the sleeve of my clothes. I'm going to rub it so well. By rubbing it very well and taking it up to another paper, a very thin paper, it might be wide, it might be small. This thing can definitely pick up the paper even without contact between the both of them. That means there is a force exerted on the paper. That is the electric force. So physics is about 2 under electricity. We call one or under electric, let's just call it electros or electrics or electronic. We call one electrostatics. We call one electrostatics. Electrostatics involve, I would like you to be jotting things down, guys. Electrostatic involves the study of electric charges while they are static. While they are static. What do we mean by they are static? When they are not in motion. When they are not in motion, that is electrostatic. So electrostatic is a branch of physics actually. The most early branch or the earliest branch of physics under electricity. It wasn't of much practical use before, but later they discovered the importance of this part of physics. Electrostatic is the study of electric charge that are at rest. Static electric charge. The study of electric charge that are at rest. While when the electric charge starts moving, we call it another name. That is electricity. Electricity or current electricity. That works with moving charge. When there is charge that is moving, I'm sorry, so when there is motion of electric charge, then we can say that electricity is the one we're talking about. So I would like to have the modules, the units we'll be talking about. So I think this is enough of an introduction now. Just take the sense and the words. So, electric charge, Coulomb's law, principle of superposition, electric field, and conclusion. Okay, so there is one common thing that we use to describe electric charge. A common thing we use to describe movement of electric charge. We are having two things here. The first one is ebonite rod. So ebonite rod is here. Another one is glass rod. These are the 4 elements we'll be using. They are not chemistry elements. I mean the 4 things we'll be using. So ebonite rod, glass rod, ore, and silk. We all know what these things are. Now, the basic concept is that ebonite rod, when it's been rubbed with 4, let's say this is a 4, and this is an ebonite rod. This is a 4, and this is an ebonite rod. So when the ebonite rod is being rubbed with 4, it acquires a charge, and that charge is negative charge. So when an ebonite rod is rubbed with 4, it acquires a negative charge. That is the basic concept of ebonite rod and 4. The ebonite acquires a negative charge. So now, this is another rod. It is a glass rod. And this is another material. It is silk. Silk. So when glass rod is rubbed against a silk, rubbed with silk, the glass rod acquires a positive charge. The glass rod acquires a positive charge. A charge is produced on the fall by what? By friction. We call it friction. Though it's not that it's hard to move on it or stuff like that, but we describe it as friction. It is caused by friction. That's what we used to describe it. We have ways of producing electric charge. We have friction, and we have induction. So now, this is for the friction. And now, this is my ebonite rod. This is the fall. So rubbing the ebonite rod with fall, I saw some questions like this, and people are sending them to me from their TMA. So an ebonite rod rubbed with fall makes the ebonite rod to acquire a negative charge. These are common questions. They will definitely come out for exams, stuff like this. Why a glass rod, when it's rubbed with silk, acquires a positive charge? When a glass rod is rubbed with silk, it acquires a positive charge. So now, the basic concept now is that an ebonite rod that is negatively charged and a glass rod that is positively charged, when they are brought together, when the both of them are brought together like this, a force occurs between them. That force is known as the force of repulsion. They will repel each other. The ebonite that has acquired a negative charge and the glass rod that has acquired a positive charge, when they are brought towards each other, they repel each other. They attract each other. I'm very sorry for that. They attract each other. Sorry. Please, listen very well again. They attract each other. They didn't repel. They attract each other. That is, the negatively charged ebonite rod and the positively charged glass rod. When they are brought together, they attract each other. They attract each other. But if I have a negatively charged ebonite rod with another negatively charged ebonite rod, exactly the question that I am talking about. A negatively charged ebonite rod with another negatively charged ebonite rod brought together, they are going to repel. I know there are people that are very, very smart here. I have Jeffrey here. I have Andrew here. I have Aminat here. I have Joy here. I have Naomi here. I'm very sure I have so many people that are quite smart here. And even people I can't even mention their names here.
And Raphael too.
Mr. Ime, you are here too. Sure. Very smart actually. So, and some other people I can't mention their names. So I really can't see everyone's name. So I believe you guys should be able to be deducing it small, that an ebonite rod brought towards a glass rod. Don't forget, the ebonite rod acquired a negative charge. The glass rod acquired a positive charge. While the both of them are brought towards each other, attraction occurs. Now, another ebonite rod is brought towards this ebonite rod. This is the other ebonite rod. Now we have two ebonite rods together that are negatively charged. They are both rubbed with 4, which made them negatively charged. Now they are brought towards each other. Then there is a repulsion. This one repels this one. They are of the same nature, the same charge, that is negatively charged. So they repel each other. They don't want to meet each other at all. They go against each other. Also, I'm left with another glass rod with, I'm left with this glass rod and this glass rod. They are also what? Repelling each other. There is repulsion between them. Now look at it. I'm very sure you've gotten the law. Ebonite rod and glass rod. They are differently charged. They attract each other. Ebonite rod and ebonite rod repels each other because they have the same charge. glass rod and glass rod repels each other. That thing, because of that experiment we just performed now, the scientists were able to predict, or sorry, to state one law. So now I want you guys, one of you guys, to tell me the law, and I want you to state it. Don't even forget about the way they stated it. You just bring it the way you understand it here. So anyone, Mr. Nwabiu, sorry.
Ochuku. It's the law. It's the law of force.
The law of
Force.
the law of force. Oh, I'm going to deduce that you are very smart, but you haven't heard of it before. So it means you are even very smart. You really tried. Okay, you said the law of force. Listen to me again. For those of us that haven't even gotten it very well, this is an ebonite rod, negatively charged. This is, you can listen to me mentioning charge. Negatively charged. This is a glass rod, positively charged. When they are brought together, they attract each other. Now, these are two.
I don't know what happened to his network, but the law he's trying to ask us. What's the law we can deduce from that observation is that like charges repel each other, but unlike charges attract each other. That's just it.
I think he's talking about the charge conservation law. That's the law he's trying to talk.
It's actually law of force between charges. That's just it.
Yeah, law of electric charges, and the law was stated by Coulomb's law of electric charges. Like charges repel each other, while unlike charges attract each other. He has explained this thing before now.
And it works the same way between all types of forces, magnetic force, all of them.
Hello, class ended. Okay, class class just one start. So as the class ended, wow. Are you kidding? We have a lot to do. We have a lot to do actually. I don't want us to die on the road this semester. I want us to take it to somewhere. So they are still doing small boy play. Very now. Okay, Jeff, let's hear from you. Oh, because of time. Because of time. So we call this law the fundamental law of electrostatic, or fundamental law of static electricity. We call it law fundamental law of static electricity. And according to what we just okay. So because the law fundamental law of static electricity. And according to what we just explained now, we can see that the law says that like charges repel, because positive and positive repels each other, while unlike charges attract. Positive and negative attract each other. The silk attracts the ebonite rod, but the silk repels the silk. The ebonite rod repels the ebonite rod. So ebonite rod and ebonite rod, they are light, while silk and silk, glass rod and glass rod, they are light. So the ebonite rod attracts the glass rod because they are unlike, while glass rod says that 2 points. Like charges repel, while unlike
Sorry, Ali,
charges.
sorry. Please, we stopped hearing you.
You're not hearing me.
We stopped hearing you for about almost a minute now.
Okay. I think it should be okay now. It will be okay now. It's just fluctuating small. It will be okay now. It's quite stable now. I said the law says that like charges repel, while unlike charges attract. That's why when we brought an ebonite rod towards a glass rod, the ebonite rod was negatively charged due to the force that is being rubbed with. So it became negatively charged. The glass rod became positively charged because it was rubbed with the seal. So they have different charges. That's why when they encounter each other, they keep attracting. So, but when I bring two ebonite rods together, this one and this one, they are both ebonite rods. So that means they have acquired the same charge from the before. So then they will repel each other. So like charges repel, while unlike charges attract. That is it. That is the fundamental law of static electricity. Okay. I Yeah, I'm not saying anything now. I'm not saying anything. I'm seeing your text. I'm just having some small issues here. It's okay. I'm very sure you are hearing me now. I wasn't talking when you were hearing me. So don't stress yourself. When you were hearing me, I wasn't saying. So you can unmute your mic. You can unmute your mic, yo. Okay. So now, that is the fundamental law of static electricity. It's a common law, and you'll be asked. You might not be asked to state the law. The law might not be given to you to complete, but they will ask you. The way I met the question exactly I'm talking about, the person sent it to me. It says, when two ebonite rods are rubbed with 4, the now brought option. The force between them is repulsion. The force between them is inspiration. The force between them is attraction. And the last option, all of the above. Is there anyone that can answer the question? When two ebonite rods are rubbed with 4, when two ebonite rods are rubbed with 4, A, the force between them is repulsion. B, the force between them is attraction. C, the force between them is inspiration. While D, all of the above. Is there someone raising his hand? Repulsion. Thank you very much. Who's this again? Prodigy. Thank you very much. Okay. I would like you to. All right. So that's good for everyone. I don't know if there are still some people that didn't get the concept, but this is the law. You shouldn't waste much time on it. So the next thing is conservation of electric charge. Originally, this thing was my old ebonite rod earlier, right? And this was my glass rod. Before I rub this thing against fur and silk, they were chargeless. That is, the number of proton there is the same as the number of electron. There is no transfer of electron already. There's no transfer of electron. So they are neutral. They are neutral. I don't want to enter chemistry. I would have explained it with chemistry. Why an atom is neutral when they say this one is electrically neutral. But I will only be wasting much more time. That's why. So originally, before I rubbed this thing with 4, and before I rubbed it with 4, it didn't okay, look at it. This is my ebonite rod. This is my glass rod. I did not rub them with anything. Is there any repulsion? No. Is there any attraction? No, because no charge was lost or gained by them. No charge was lost or gained by them. But after rubbing it with 4, this one attained a particular charge. And after rubbing it with silk, this one also attains some particular charge. So this one becomes positively charged. This becomes negatively charged. So what we are now talking about when talking of conservation is that when we add the charges together, the algebraic sum is going to be 0. It's like saying this one attained a charge of -1, and this one achieved a charge of +1, because one will be positive, one will be negative. Listen, I have 2 things. The charge that leaves this one is entering this one. The charge that leaves this one is entering this one. So this one is taking charge from this one. Okay, let's say, listen very well. You are going to get it now. Let's say the 4 now has a charge of 8. So let's say 8 electrons. The 4 has 8 electrons. And now, this one too. This one has 7 electrons. The ebonite rod, please listen carefully. The ebonite rod has 7 electrons. The 4 that I'm rubbing it against has 8 electrons. After I rub them against each other, the 4 lose 2 electrons. It remaining 6 electrons. And the ebonite rod, this one is losing 2 electrons. So where is it going? It's going to this one that is rubbed against it. This one gained 2 electrons. The 2 electrons that the ebonite rod is losing is being gained by this one, right? So this one gaining this one makes it 9 electrons. That is, this one 2 plus, what is it? 2 plus 7, 9 electrons. Are we moving together? Let me see with reaction if I should go back and explain this thing now, before I finish explaining it. Great.
Please go back home.
Okay, sir. I said F is representing the 4. That 4. Rabbit 4. Like 4, stuff like that. So, and the E is representing my ebonite rod. Originally, before is rubbed with the ebonite with the ebonite rod. So the ebonite rod acquires some charge. It becomes negatively charged. Charge is transferred from the 4 to the ebonite rod. So I'm saying that the 4 is transferring 2 charge from itself. Transferring 2 charge from itself. And that 2 charge is being transferred to the ebonite rod. What was 8 before? Ebonite rod was 7 before. Losing 2 charges, it becomes 6 electrons. And this one, taking 2 charges that is being lost by this one, it becomes 9 electrons. How many charges did this one lose? 2. So, how many charges did this one gain? 2. But don't forget that the one that is accepting the electron will become negatively charged. We said an ebonite rod rubbed with 4 is going to become negatively charged. And the one that is giving the electron will definitely become positively charged. The one that is giving the electron out becomes positively charged. So they are both two values. But when we look at the integers, they are whole numbers as 2 now. But the integers are -2 and +2. That is the difference between an integer and a natural number or a whole number. So when we're now talking about the algebraic sum, we need to work with their sign too. That's why they mention it, and they will always emphasize algebraic sum means +2 plus -2. And that gives what? 0. Therefore, in a closed system, the amount of electric charge given out and the amount of electric charge taken in, their algebraic sum equals 0. That is, no charge is created, no charge is destroyed. The algebraic sum gives 0. That is law of conservation of charge. Law of conservation of energy says energy can neither be created nor destroyed. Law of conservation of momentum. The momentum before is the same as the momentum after. Law of conservation of mass. Mass can neither be created nor destroyed. Stuff like that. You understand? So I just explained the law of conservation of electric charge now. I would like you to go over the video if you didn't understand this. I won't go back again. I wish you the best. Okay. Law of conservation of electric charge again says that in a closed system, then the algebraic sum of the lost electron or lost charge and the gain charge gives 0. Loss, this one is losing the charge. It's not like it is destroying it. It is only moving from it to another place. This one is gaining it. When you add them together, 0. If it gives you 1, then the law is not obeyed. There is no way. The law will always be obeyed. According to Newton's theorem, this law will always be obeyed. But by everything is conserved. Even in the universe. I explained some things. I said we have open system, we have closed system, and we have isolated system. I won't be going on to that. I wish you the best. Let's enter quantization of electric charge. Thank you. That's great. I'm happy to see that. You understood it. Quantization of electric charge. Quantization of electric charge simply says one thing. This thing is discrete. Finish. It is quantized. When we say something is quantized in physics, it is discrete. It is not continuous. That is, all charges in this world, the smallest charge known is the charge of an electron. Electron is negatively charged. It's the thing that spins around the nucleus. Even though some scientists are telling us now that it doesn't really spin, and I think I believe that too. I listen to the explanation that the electron actually doesn't spin around the nucleus. Yeah. So, but let's give our own explanation that way. Yeah, at least. Okay. I don't know. It's not so easy for me viewing the messages. Okay, let's go, guys. I don't know why I'm having two accounts here now. It's giving me an issue. I don't know why. And this is the one I'm supposed to be using originally. I'm calling. It's no network. I think I should be hard now. Can you all hear me now? Prodigy.
Sure, we can hear you.
I'm sorry, it's really not network. I don't know. Whenever income messages come in, I would like to check it out that was there. So my brother couldn't grasp it once and for all. So I had to go and check. And I don't know why I'm entering another account. So E is the electron, right? So when we're talking about electric charges being quantized, the smallest charge known, there is no other charge at the moment that is smaller than electron. Normally we have the quantum realm, we have the antimatter realm. So, but for the subatomic things now, even after that, the smallest charge known so far has been the charge of electron. Now, what they are telling us from quantization of electric charge is that there is no charge smaller than the charge of electron. And after that, all other charges are a whole number multiple of the charge of electron. There is no fractional multiple of the charge of electron. You can never see 0.7 E. You can never see 3.5 E. You would rather see 7 E, 3 E. That is the meaning of quantization of electric charge. That is, it is quantized, it is discrete and not continuous. Continuous as in 7.1, 7.2, 7.3, 7. No. There's nothing like that for electric charges. The charge will rather be a whole number multiplied by the charge of an electron. The charge of an electron, if you would ask me, would be 1.6 times 10 to the power of minus 12 minus 19. 1.6 times 10 to the power of minus 19 coulomb. Yeah. This is the charge of the electron. I wanted to write minus 12 microcoulomb before, minus 11 microcoulomb. So minus 13 rather. So this is the charge of an electron. Very well known charge of electron is 1.6 times 10 raised to the power of minus 19 coulomb. So all other charges, like the charge of neutron now, would be a multiple of 1.6, a whole number multiple of 1.6. That is, if you, I cannot check that in you sent again, please. Can you please, if you have something to say, just raise your hand. I can't really be checking those things. You can see I'm far from the phone. It's not convenient for me at all. Please just raise your hand and you'll be given the permission and go. So now the formula is Q equals NE. I also encountered questions like this. Yeah. Prodigy, if you could remember part of the questions I sent that night. So this is one of the questions. The question says that no. The question says that the quantity of electric charge is given is I think 3.2 times 10 to the power of minus 19 coulomb. So what is the multiple? What is the whole number multiple of the electron there? So this is the Q given. The N is what you don't know, and the electron charge might be given, you might not be given. It's always 1.6 times 10 to the power of minus 19 coulomb. What do you do? Q equals NE. What are you looking for? You're looking for the N. Then N equals Q over E. That is the ratio of the charge given to you to that of the electron. That is 3.2 times 10 raised to the power of minus 19 coulomb over 1.6 times 10 raised to the power of minus 19 coulomb. This is going to give me 2. So the N has the value of 2. You can see it is a whole number, not 2.5, not 2 point. So having whole number is what we mean by quantization of electric charge. Did I explain that? That is, all other charges you'll be encountering must be a whole number multiple of the charge of electron. Every other charges you will be encountering would all be a whole number multiple of electron. They are discrete and quantized. They are not continuous. It will be 2 point something times the charge of electron. It would rather be 2 whole number times the charge of electron. That is it. Let me give you the figure. Sorry. Let me give you the statement. It is that all other charges would be a whole number multiple of the electron, and there is no fractional multiple of the electron and charges. No fractional multiple. Like 1/7, that is 7/10 rather, 0.7, 3/5, 0.6. This, no. There is no fractional multiple of electron. That is that as quantization of electric charge. Okay, talking about one thing again, because I want us to finish that whole thing today. I want us to enter Gauss's law this night, because I could remember that I think at the beginning of the semester we touched stuff like this. So I don't want it to be what we are going to touch for this full night too. I hope the time doesn't go too much. I want to touch Gauss's law a little bit. Okay. Coulomb's law. A very simple law. Look at me. I'm going to illustrate it with 2 small things. Note this, everyone. I will call these things point charges. They are not point charges, but I will call them point charges. I'll call them point charges. They are in space. They are in existence, right? These 2 things. One is here. Mark the point. One is here. Let's trace it here. Please, everyone, note what I'm doing. Don't let me do it in vain. Please, you must understand. One is here. So to make it visible. And the other one is here. So let's make it more practical. So let them understand very well. The other one is here. So this is the one here. This is the other one here. In space. This is a charge, a point charge. This is another point charge. Now, forget about the fact that this one is positive charge, this one is negative charge. The thing you should know is that at least there is a distance between them. Do you agree with me? The distance is r. The distance between them is r. And after there is a distance, now I want you to forget the law of static electricity, paramata. Forget that law now. Forget that they are not attracting each other, they are not repelling it, forget it. Now, forget about repulsion and attraction, that is what I mean. For 2 things that are like this, there is definitely a charge existing between them, a force existing between them. I'm going to call that force F. Force F is the one existing between them. Abdullah, any issue, anyone? Is there any issue?
No, continue.
Okay, I think that person is not getting it. Williams, I'm coming again. I'll check. Okay, I said this is the first charge. We call them point charges. I will assume it is proton. Don't let me make that up. Let me make that. No, I don't want to make it so obvious now. I want you to be understanding it by yourself. So it is a point charge. Forget about the charge, positive or negative. This is another point charge here. They are separated by a distance r. By chi. Do you have anything to ask? All right. So, and there is a force that exists between the both of them, the force F. So, because of this, the square inverse law came first. That is part of the Coulomb's law. So, you know, Coulomb's law is broken into 2. Square inverse law. That is, the force here is inversely proportional to the square of the distance between them. This is the meaning. That is, when they are closer, like this, then the force between them reduces. That is, okay, the force between them increases. That is it. Yeah. So look at the both of them like this. They have a force that exists between them. But when they are closer, the force becomes small. Do you know? It's like having two magnets. The magnets might not be having effect on each other until you bring them closer to each other. So when they become more closer, the force becomes small. That is, the distance becomes smaller, the force becomes bigger, larger. Seriously, I'm experiencing magnetism from this thing. Very funny. So now, and when we keep taking them apart, then the force becomes weaker. The distance becomes larger, the force becomes weaker. That is the essence of inverse proportionality. We all know law of demand, right? Thank God, you later got it. So the force, the higher the force, the higher the distance, the larger the distance, the lower the force. The lower the distance, the higher the force, the larger the force. That is what we mean. That is inverse square law. So the inverse square law was now worked with. Let's say this charge 1 is Q1 and this charge Q2 is Q2. Column now join them together later. That the force F will increase. Okay, let's put it that way. Due to the charges on these two bodies, 2 points here, a high charge, highly negative, highly positive, or even just high charge, like 1,000 coulomb, 1,000 coulomb. Are you with me? 1,000 coulomb, 2,000 coulomb. You can see they are very high charges. So that means if these two bodies, two charges are very high, they have high coulombs, then the force between them becomes larger. But having 10 microcoulombs, the force becomes weaker. That is, the higher the magnitude of the charges, the higher the force. Do you know, this is somebody. Look at how wide he is. I think I'm a little bit taller than him. So the both of us coming against each other, you should believe if we jam, the force should be very big, right? And compare us to two infants, a baby girl and another baby girl, jamming each other. You shouldn't be comparing the force. So the higher the force, the higher the magnitude of the charges, the higher the force. That is why those ones are directly proportional. But the higher the distance, the lower the force. That is why that one is inversely proportional. So I'm going to state the Coulomb's law. I know there are some technical people here that have understood this one. It's just to explain it to the technical ones. For those of you that are not so technical, listen. It says that the force that exists, it might be the force of attraction, it might be the force of repulsion. Between 2 point charges, that is Coulomb's law, I'm stating it for you. The force that exists between 2 point charges, the force F, let's be pointing them out. The force F, these are the 2 point charges, Q1, Q2, separated by a distance R, and exists between them is the force F. So the force F between 2 point charges, separated by a distance R, 2 point charges separated by a distance R, that force is directly proportional to the product of the charges. Product means Q1 times Q2. Product of the charges, we're going with that, and inversely proportional. Inverse proportionality means proportional to 1 over square of the distance between them, R squared. This is Coulomb's law. This is Coulomb's law. Hey, how come nobody is reacting? Nobody got it right in here. This is Coulomb's law. I trust my guys now. So the force of either attraction or repulsion existing between 2-point charges is okay. Is there, please, who's the person using crying emoji? Let's hear your issue, please. You don't understand it? Who's it? Let's know, please, before I proceed. We're all here together. No response. Forget it then. So, the force that exists between 2-point charges, the force that exists between 2-point charges separated by a distance r is directly proportional to the product of the charges q1 times q2 and inversely proportional to the square of the distance between them. Doing the mathematics here, I'm going to have fr squared over q1, q2 equals to k. Doing the mathematics of joint variation. This is a topic in math, joint variation. Because some people might not understand it here. That's why I won't be doing it here. I'm only going to write the formula derived from this thing out. I don't want to enter maths and be wasting our time. So at the end of the day, we are going to have F equals to K Q1 Q2 over R squared. We call this the Coulomb's law. This is the mathematical representation of Coulomb's law. This is the equation of Coulomb's law. Great. So we call it the Coulomb's law. F equals KQ1 Q2 over R squared. K times this is the mathematical representation of Coulomb's law. F directly proportional to Q1, Q2, and inversely proportional to R squared. Mathematical representation of Coulomb's law. I just showed you what S is now, F is now. The R I just showed you, Q1, Q2. Mind you, the force could be a force of attraction, and it could also if they are of the same nature, that is positive and positive, to be repulsion. Negative and negative, it will be repulsion. Positive and negative,
I beg,
it will be a force of
explain that
attraction.
Explain that to I beg.
I should explain what I just mentioned now. Okay, yes. Jeffrey, you shouldn't compare yourself to everyone here now. You know, I must be breaking things down. You understand, bro? So you just want me to enter K and I should be explaining this small now, bro. Because some people will say they didn't understand or stuff like that. Okay, this K now is a constant, or it is the constant. It is the constant of proportionality here. It has the value 1 over 4 pi epsilon naught. This is the Greek alphabet, epsilon. So because of this 0 here, so we call it epsilon naught. Epsilon naught. So K is, that K here is having the magnitude of 1 over 4 pi epsilon naught. Why are we using 4 pi? Because it exists in always symmetrical things, spherical symmetric stuffs. So that's why it's hard to explain now. But this thing here, this epsilon naught, is a value. We call it the permittivity of free space. Permittivity of free space, or the free space permittivity. The free space permittivity. Please be jotting these things down. They are, you know how noun questions are naughty questions. Naughty questions. You just be like, I passed through this thing. Then why can't I answer it? So it is known as permittivity of free space with the value of, it has a value, and the value of this is 8.98 times 10 raised to the power of minus 12 coulomb squared per Newton per meter squared. This is the value of epsilon naught. Are we together? You can put it somewhere. It is free space permittivity. So there is every value for, there is the permittivity for all medium or all media. This is permittivity of a vacuum, free space. Permittivity of air is very close to it. That is 1.005 times permittivity of free space. So that's why they represent it as the permittivity of air sometimes. So there is one thing we also call permeability. We are working with permittivity here. The unit is coulomb squared per Newton per meter squared. It also has another unit which is very common when working with capacitance. The unit is farad per meter squared. Farad per meter. Farad per meter. No, it is farad meter. It is farad meter or farad per meter. It is farad per meter. Sorry, don't want to confuse you. Meter. It is farad meter. Farad meter. This is another unit for epsilon naught. So we call it the free space permittivity. So we've written the Mr. Amy, any question? Any question, sir?
Sorry, you said something about this epsilon naught. I didn't get it.
Okay. I said it is the free space permittivity. So what is free space? Free space is vacuum, a place that is not occupied by anything. There is no matter in it at all. There is no air, nothing.
Okay.
That is what we call free space. So the permittivity of that free space has the value of 8.98 times 10 raised to the power of minus 12 coulomb square Newton per Newton per meter square. So if it's not about, it's because it deals with free space. If it's not about free space, when you enter in this course, we'll still be getting there. You'll be saying that we are not using it as, so we'll be using relative permittivity. So depending on the nature of that medium, because this one medium is what? Free space, vacuum. Like saying the speed of light in a vacuum is 8 times 10 to the power 8. So the speed of light in glass is this speed of, you understand? So that is what we mean by these two. So we said Coulomb's law is F equals K Q1 Q2 over R squared. So what is K? We came here and said 1 over 4 pi epsilon naught. So F is going to be, please, I don't know, I think I'm too fast. I'm going gently now. 1 over 4 pi epsilon naught. So Q1 Q2 over R squared. So this is the best way to write the law, the equation. Instead of writing K, write 1 over 4 pi epsilon naught. But when you start calculating, instead of stressing yourself and going through this, that's 1 over 4 times 3.12 times 8.89 times 10 to the power minus 12. They solve this thing for you. They already help you to get the value. Are you with me? They already got the value for all these things for you. This K, they got the value for you. They calculated it for you. And they had K to be 9 times 10 raised to the power of 9 Newton meters squared per coulomb squared. 9 times 10 raised to the power, it was actually 8.99, but they approximated it to. So 9 times 10 raised to the power of 9 Newton meters squared per coulomb squared is the value of K. We are working with all these values. Don't neglect them in any way. You might not be given an exam, and you might be given. It depends on how lucky you're gonna be. Okay, are we moving together? If you understood all what I just explained, all the blah blah blah, let's see it somewhere. Hey, thinking about it somewhere. Yeah, the truth. Okay. I said the K here now is being represented by this thing, 1 over 4 pi epsilon naught, written here. Instead of writing K, I'm writing 1 over 4 pi epsilon naught, Q1, Q2 over R squared. So, you know, when we enter workings now, you might be given Q1, Q2, R squared, look for F. You'll now be thinking you should be looking for 4 pi epsilon naught by yourself too. No, they're giving you the value of this one. So when you are solving, you just write 4 pi epsilon naught, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught. Everything together. Just write 9 times 10 to the power of 9 times, what is Q1, Q2 over R squared. That is what they are telling you. That is what we are telling you here. So did you get it now, Mr. Tochukwu? Did you get Mr. Tochukwu, please? All right, that's great. So instead of looking for, it's because permittivity is having another value. It is very important. That's why I gave the value here. It is not the value you'll be using to calculate it here. Don't forget. This is just the value of free space permittivity. This is the value of the whole constant in Coulomb's law. Okay, they call it the Coulomb's constant. The K is Coulomb's constant. That is Coulomb's law. Let's take just an example to solve. The law is
Ali,
written out. The equation is there. You can write it out first. You use it to solve this question for me. Bro, any issue?
is it 9 times 10 raised to power 9 or
Yes,
9 times 10 raised to power 10?
It's 9, 9, 9. 9 times 10 to the power of 9.
Another thing, when did they approximate the value? Because I know it was 8.888 something.
It was 8.98. It was 8.98.
8.988 something.
Times 10 to the
So
power.
they always approximate it.
They approximated 8.98 to 9 straight away.
Okay, but if somebody uses that 8.98?
Exactly, yeah. That's it.
If I use that 8.98, you know wrong, Abi?
You know me
It's
now.
not bad.
I don't get exactly the answer they are getting. You know, there is a difference of 0.000000001 here. So that's it.
Okay,
There's
that
a
means to
difference.
get on the better side, we should use 9.
And sorry, Ali. Sometimes too, they can give us that 8.98 too. You can make use of that 8.98 if you are
If
given.
you are given, don't make use of another thing. If you are given that 8.98, make sure it is the 8.98. Yes.
Yeah, because in most of the questions I've seen, they give K constants as 8.98. So that means if they don't give it, we can just use 9.
Yes. Now, is it Tochukwu? Mr. Tochukwu, are you the one raising your hand? Any question?
Yes, please. Just a quick one. So according to what you are saying, the constant is the 1 over 4 pi epsilon naught.
That is the Coulomb's constant. K, yes.
Okay, so if you are to denote it in figures, it could be 9 times 10 raised to power 9.
Yes, very well.
Okay.
And note, it's not 1 over. It is
I said 9.
So I'm telling you because of some other people. So I want other people to see.
Thank you.
Okay. You're welcome.
Please also take note of the unit too. Newton per meter square per coulomb square.
That's it here. Newton meter squared per coulomb square. Newton meter squared per coulomb square. That is K. Newton meter squared per coulomb square. And M squared per C squared. Okay.
I cannot hear.
Newton coulomb square per meter squared. I think it's your own network. All right, let's just continue. I have a question let's say I'm having, find the force and tell us the nature. Find the force that exists between two different charges find the force. Okay, write the question down, please. I'm thinking of how it's going to come. Find the force that exists between two different charges of 10 coulombs and 15 coulombs separated by a distance of 10 meters. Given that K is equal to 9 times 10 to the power 9 Newton meter squared per coulomb squared. Okay, let's see the fastest solver here. I'm waiting for you guys. And also, after that, and what is the nature of the force? I want to see how technical you guys are. What is the nature of the force? Is it a force of attraction or a force of repulsion? Okay. Because of what I'm doing, let me add something here. Two different charges of 10 coulombs and minus 15 coulomb. Note that. Minus 15 coulomb. What did you say? I don't know why. It's your own place over there, Miss Chi or Mr. Chidogo or Diogo. It's over there. You are going to watch the recording. Don't worry. Okay, I'm waiting for you guys. Anyone with the answer? Don't neglect the negative sign here. Jeff, Prodigy, Inksmith, Aminat, minus
Yes, I got 1.35 centimeters.
What is the first? I think I saw what Prodigy wrote. Another person? I'm waiting for you guys. Solve it. You have the formula with you. It's just a simple evaluation you're going to do. A normal evaluation. Force of attraction. Prodigy, the technical guy. It's plenty. He will tell us the reason later. Mr. Edward, I greet you, sir. All right, can you hear now, Mr. Chidiogo or Miss Chidiogo or Mrs.? All of you, is this one standard form? A whole scientist like you, Jeffrey. Share a standard form with that one. Your standard form is still having 13. 13 is more than 10. Why not put it as 1.3? Let's see the edited version, Jeff. Yes, that's it too. It's that when it's already in standard form, it must be less than 10. 13 is more than 10. Okay, I have 4 people with the answer here. We'll solve. Please, let's see about 2 more people. Oh, are you guys not solving it? It's I don't know if negative, but you go for repulsion. Okay, you judge yourself if you were correct or not. Let's solve it, guys. Solution. There are sometimes solo has to be key. So, but no, there is addition. Who knows? Or solution, like so too simple. It's so very much too simple. Okay, the law is F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared, right? So 1 over 4 pi epsilon naught is 9 times 10 raised to the power of 9 times Q1 is what? 10 coulombs. Q2 is what? Minus 15 coulombs. All over R is what? 10 meters. That is 10 squared. Okay, we can keep going now and say we have minus 150 times 10 raised to the power of 9 minus 2. Normal indices. 10 raised to the power 9 and this 10 raised to the power 2. 10 raised to the power A raised to the power B divided by A raised to the power C equals to A raised to the power B minus C. So 9 minus 2. So this is minus 1.5 times 10 raised to the power of, this is 7 plus these 2, 9. So minus 1.5 times 10 raised to the power of 9 newtons. That is the force. Your unit is even more important than your value. But yes, what is a unit with a value without unit? Useless. I won't even be able to tell, is it force you are looking for, or charge, or capacitance, like this. So the value is minus 1.5 times 10 raised to the power of 9 newton. Let me tell you, if the force that exists between them is negative, just know that it is a force of attraction. So prodigy is technically correct. Very, very correct. So if the force that exists between them is negative, then it's a force of attraction. If the force is positive, this 9.
Ali, wait, though. What you saw is wrong.
What of your 9?
No, he
My
added
9,
Don't
the
forget
nine. He added the 9 with everything and divided it by 10 raised to the power 2.
That's what my brother
You are
is.
supposed
Sometimes you just carry eye from me that this boy. You understand? So let's just do it. 9 times minus 15. That's going to give us what? Yeah, fast.
that's 135 minus 135.
So minus 135. That is now okay. Minus 1350 times 10 raised to the power of 7. So minus 1.35 times 10 raised to the power of 1, 2, 3.
That would be 10. That would be 10.
I've forgotten there was 9 there. That's what my brother is telling me exactly right now. Oh, God.
Is it raised to power 10?
Yes.
7. Yeah, Jeffrey. It's raised to power 10.
Oh, wow. This
Yeah, I do approximate mine. You are correct. Yeah.
So if it's positive, then it's going to be a force of repulsion. Moreover, you are given already that minus 15 coulomb and 10 coulomb. You can see they have different charges. Just know by yourself that the force that will exist between different charges, according to the law of static electricity, is attraction. Is attraction. Coming? So that's that as for that. Let's keep going. It's only prodigy that's now my guys see now let's see other people. All of you that are answering like this, all of you have do this before. Please, another person, let's see. Mr. Ridwan, did you understand it?
Not too clear.
Not too clear. Let me explain it. Sorry. I want you to be able to cover. Naomi. Is it Naomi? Naomi,
Yeah.
are you the one?
No.
Is it your own, Naomi? Okay, it's not your own. Okay. Okay. But the voice is no worry. I'm gonna come back here later. Mr. Ridwan, go over it, look at it again.
Oh, Ali, she will break your head today. But I don't go talk.
I don't want to wait around. I just they cry. Let's see, Sha. I will call her. So F is 1 over 4 pi epsilon naught times Q1 Q2 over R squared. So 1 over 4 pi epsilon naught, all this value is given to the 9 times 10 raised to the power of 9. So that is here. Sorry, one. Times Q1 is 10. Q1 is 10 coulomb. Times Q2, which is minus 15.
Okay.
All over the distance between them, R That is 10 meters, 10 squared. Here it is. So after doing that one, just leave judgment to your calculator. You're going to get this. Minus 1.35 times 10 to the power of 10. But let me tell you very well, do the numerator first, get the answer of the numerator. Do the denominator first, get the answer of the denominator. Divide the numerator by the denominator to get your answer. And here I will have minus 1.35 times 10 to the power of 10 newtons. It is negative because the force is a force of attraction. If it was positive here, then it would be a force of repulsion. That's that as per Coulomb's law. Thanks for your concern. Thanks for your concern. I don't know. Check. Maybe I don't know if he's going to reply or she. Thanks for your concern, Mr. Kochuku.
But what if they give the distance in a unit different from meters?
Meters. So you just change it to meters. You are given the distance in kilometers. Just change the distance to meters. To change from kilometers to meters means multiply it by 1,000. If the distance is given in millimeter, that means change it from millimeter to meter. Divide it by 1,000. I'll do that thing now. I'll do it now. Let me rub the bottle first. I'll do that now. Chi, do you still have something to say? I think you haven't seen a breakthrough about this. I wish you the best. Let me quickly do the ratings for you. It might be useful for some people. We have centimeter. Normally, meter is the unit. We have centimeter. We have the value. We have decimeter. We have the value. We have. Let me start from. How am I going to put it? Yes. Let me start from centimeter. Decimeter. 10 decimeter equals 1 centimeter, right? So
start from millimeter.
I'm taking it downward. If I start from millimeter, I won't be able to mention this one. I quite know what I'm doing here now. And start from decimeter. I would like you to note them. Start from decimeter, after then centimeter, after then millimeter. You can see if I start from millimeter, I won't be able to measure this. After millimeter, micrometer. After micrometer, nanometer. After nanometer is gonna be picometer. After picometer is gonna be nanometer. I've forgotten it. 10 to the power minus 15. And I actually happen to forget it. I knew it before. Nanometer or diameter. So this anything, you can call it diameter too. So decimeter is 10 raised to the power of minus 1. That is 0.1. So if you are given the value in decimeter, you want to convert it to meter, you multiply it by 0.1. That is common for everything. Even if it is in decifarad, you want to convert it to farad, multiply it by 0.1. I'm giving you what you'll be multiplying by them. You have a formula to change it to SI unit before. Changing something to SI unit. If you know about the unit factor. So the unit factor is 0.1. Centimeter means 10 to the power minus 2. That's why if we have 100 centimeter, we will know it is what? We will know it is 1 meter. So multiply it by 0.01. If you add millimeter, that is 10 to the power minus 3. Multiply that value given to you by 0.001. If you add micrometer, that's 10 to the power minus 6. I know somebody is planning to ask me 10 to the power minus 5. I don't know. So that's 0.0000001. 1, 2, 3, 4, 5, 6. 7. So now, yeah, nanometer is 10 raised to the power minus 9. Don't ask me 10 raised to the power 8, minus 8. That's 0.1, 2, 3, 4, 5, 6, 7, 8, 9. So by multiplying this thing by that value given to you, you will turn it to meter. Hope I'm making sense. Guys, hope I'm making sense. It's not part of our work, but it might be useful at least. If you happen to understand it, it might be useful. Picometer is 10 raised to power minus 12. I claim me say I don't remember. Is it Eka? Eka meter. It is Eka meter. No, 10 raised to power. That's positive. That 15. I'm thinking of that 15. It's positive. So this is 0.000. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the unit factors. If you want to change them to meter, like you have 7 picometer. 7 picometer is given as 7 p.m. Post meridian. 7 picometer is given as 7 p.m. You just multiply 7 by 10 raised to power minus 12. So it will now be in meter. So the value is 0.0007 meter. That's that. So there is one other very common unit they use in quantum mechanics. It is known as angstrom. Let me put it there, it might be useful to you guys. It's the same as 10 raised to power minus 10 centimeter. 10 raised to power minus 10 centimeter. Angstrom. It is represented as A that is carrying circle on its own. On its head. Angstrom. A carrying circle. One of the things I struggled upon in some old textbooks some years ago. Some very, very old textbooks. Okay, did we capture this? Is it useful? Hey, not useful. I think I've already said it's useful. I'm prodigy.
So sometimes that they call it decameter.
If it's decameter, it will become 10 raised to power minus 9. That's what it is. You know, this thing is, all these ones are negative. If it is given in after meter, given in kilometer, given in meter, in terameter, gigameter. You understand?
Yeah.
Kilometer, it will be 10 raised to power 3. 10 raised to power 6 will be megameter. 10 raised to power 9 will be terameter. 10 raised to power 12 will be gigameter. Gigameter before terameter. Giga for 9 and tera for 12. That's it, guys.
So that means those ones are above meter. Why these ones you wrote down here are below 1 meter?
This one, Abi. All these ones, I didn't hear you very well.
These ones you wrote down for now are on the minor side of meter. Why those ones, the higher ones, are above meter?
They are below 1 meter, yes. These ones are below 1 meter. That's it. They are all below 1 meter. But the ones of mega, tera are above 1 meter, kilo. Okay, let's go back to our word.
Some said you should do kilometer only.
Kilometer, okay. It's a waste of time, Charlie, bro. Kilometer is 10 raised to power 3. The hearing it if you want to write it down. Kilometer is 10 raised to power 3. So you multiply that thing by 10 raised to power 3 to change it to meter. So after kilometer, we have
multiply times 1,000.
Megameter, yes. Megameter is 10 raised to power 6. That's times 1 million. After megameter, we have gigameter. That is 10 raised to power 9. That's times 1 billion. And 10 raised to power 12. That's 1 trillion. And see, after 10 raised to power 15. That's 1.
That's diameter.
Diameter, oh. Radius meter. I know, I'm only kidding. I had you all. Oh, don't let us waste our time. Let us treat electric field. Or we can also call it electric field intensity. Electric field or electric field intensity. Naomi, before we stop this class, I go beg people, may they help me beg you. And people will stop hearing. Let's we know we are even done with the whole first unit. Electric field intensity.
I beg, this is 10:30 already. No stop. Even if let's continue.
All right then.
I will be very happy because my system will off now.
Yeah. Okay, guys. Have a nice.
Andre, switch to your phone.
Please, is this class recorded?
Kingsmate.
Mr. Kingsmate is there.
Kingsmate,
I think it's being recorded though. I think it is.
I trust my G now.
Kingsmate, I never hear
Trust
from
and
you. If these ones where they talk, they no sure.
He did there. Oh.
Naomi.
Kingsmate,
Beg never leave.
It's already on
I don't
record.
go.
It's recording. I can see the
It's
something
already
there.
on record.
Like,
okay, all right.
So once the class stop, automatically the record will stop.
yes.
See you guys in the group. Good night.
Okay, well, thank you.
Thank you, Ali. Thank you, Ali.
Jeffrey,
People go
what
chop.
did you hear me back now?
Ali, thank you. Bye bye. Good night. Go sleep. Tomorrow na Sunday.
No one be better start begging on yourself.
Thank you, Ali.
I don't start to make you log
Good
out.
night. Good
Ali,
night.
thank you so much.
May God see us through.
Amen.
Amen.
Good night.
Please, if you come next, where do we start from?
From where we stop?
I think from where we stop, electric field intensity.
We don't reach that side.
Yes, now, sharp, sharp. This is the second time for him taking all these parts now.
Oh, really?
Yes, early this year.
Yeah, I'm just seeing principle of superposition.
Who is doing there?
You take principle of superposition.
Can we call it a
You
day?
take principle of superposition immediately after taking
Good
the
night, everyone.
electric field.
Oh,
That's
that
just
was when I left to make food for my own people. Oh, damn.
I won't go church.
Okay.
Bye bye.
I
Good night.
want to end the
Go back
class,
to it.
please.
I'll go back to it.
Good night, everyone.
Thank you.
Okay.
Make that no miss me too much.